I'm sorry about the delay there. I needed to get something for Elizabeth, and it took me a little longer than I thought. Oops. That's not what we wanted. Okay, so this is, I believe, where we were yesterday when the bell rang. We had written this down. We said that reflection was when light encounters a change in medium and bounces back into the old medium. This is the law of reflection, theta in equals theta out. Does this look familiar to you? Yeah? Then we said refraction was when light entered a new medium. We said that 3 times 10 to the 8th is the speed that it goes in a vacuum, and it's going to slow down when it goes other places. We haven't really drawn any pictures, though, yet, so I want to draw these pictures so that we know it for our, like, moving forward here. So we're going to just do this kind of quickly, but I just want to make sure that we've got it all. So we did a few different things yesterday. I'm going to draw 3 different examples here. So if this is awesome, thank you. Let me know if you can't get into Canvas too, but it should work. Yeah. Okay. This is air and grass, right? And then we had our marchers that were marching straight ahead. And what were they marching into? Mud. Yeah. And in the first few cases, the ray was moving pretty straight. The ray was moving straight so that it was going exactly perpendicular to the medium change. And when they were walking in air, I don't even remember who was marching at this point. Tell me about your step size when you were in air. Was it large or small? Large-ish, right? So we're going to have, I'm just going to draw. So this is kind of like where they were at a moment, and then a little bit later, and then a little bit later. And these, we call these the wave fronts, right? This is like watching them march. And then as soon as they got into mud, what happened? Their steps got smaller. And so we would represent that with lines that are a little bit closer together. Because now their steps get closer together. And in our kind of physicsy brain, we can think about 3 things here. We're going to think about frequency, we're going to think about velocity, and we're going to think about wavelength. How did the frequency change from when we were in air to when we were in mud? The frequency stays the same. Because the frequency always stays the same when you move from one medium to another. Always, always, always. We decided that when we were marching in air versus marching in mud, what happened to our speed? What did we think was going to happen? We're going to slow down, right? The velocity is going to go down. And that is as a result of our wavelength going which way? Down. Yeah. Smaller step sizes, smaller wavelength. Life is good? So we did that a few times and had some success. And then I decided to throw a wrinkle into things. And instead of going at a straight, like in a straight line, again, I've still got the air on the top and the mud on the bottom here. So I'm going to go ahead and write that air and mud. Instead of going straight into the mud from the air, what did we do? Kind of went diagonal, like a kind of a funny angle, right? So we're going to go ahead and draw what that looks like. So that means we're going in like this. Right? I'm actually going to draw that a little bit bigger just for effect. In we go. Okay. Now, when we measure those angles and when we're trying to keep track of what's going on, remember, we're always going to use that line that I'm going to make a dotted line like this. It's perpendicular to the medium change or to the surface. What is that line called? The normal line. Yeah. Normal just means perpendicular. So in the air, just like it was before, as they march, their step size is pretty big. But then what happened when that ray, when those marchers moved from the air where they could move so fast and take such big steps into the mud? What happened to their steps? Their steps got smaller, right? And as a result of their steps getting smaller, what happened to the direction of the ray? It got closer to the normal line. It bent, didn't it? Yeah, so instead of going like this, they went, like that. Yeah. So let's go ahead and draw what that looks like. So it's going to bend in like this. Okay. And so those lines, those wave fronts, are now much closer together. Oops, I'm not doing a very good job drawing perpendicular lines. Sorry about that. Let me try again here. That's a little bit better. It's not perfect. I apologize. These should all be parallel. And I didn't do a very good job at the beginning. Let me do that again. There we go. Okay. Now, when you draw these, and we're going to do this a little bit more next week too, you don't need to draw all the wavefront lines. I just drew the wavefront lines there to help you remember that the step size changed. And as a result of the step size changing, the wavelength's changing. And as a result of the wavelength changing, the speed is changing. But we're going to write down here that in this case, what happens to the frequency? Same. The velocity goes down, the wavelength goes down, and as this happens, we're going to look at these angles here. This angle here I'm going to call theta I. This is the angle of incidence. And this one over here I'm going to call theta R. This is the angle of refraction. So it sounds kind of similar to what we were talking about with reflection, okay? But in this case, are theta I and theta R equal? What do you think? They are not. Theta I is bigger than theta R, isn't it? Okay. Or we can say that the ray bends toward the normal. One more. I'm going to do this one a little bit differently, friends, because I like to draw my rays going in the same direction. So after we had these people march from air to mud, and then from air to mud at an angle, then what did I do? We started in the mud. So I'm going to label mud up at the top now. Does that make sense? It's a little bit different, but I feel like that makes more sense than drawing my arrow the other way. So we're going to start in the mud and we're going to go to the air. I'm going to go ahead and draw my incident ray. Here it comes. It's coming in. I'm going to draw my normal line. Before I do anything else, I just want to write down a couple things. This one's a little different than this one. In this case, when I'm going from the mud to the air, what happens to the frequency when I go from the mud to the air? Nothing, right? Not a trick question, just make sure we're paying attention. The frequency still stays the same. What happens to the speed now? It's going to go up. And that's as a result of the wavelength going up. So now we've got these rays that are really close, or the wavelengths are really small. The step size is really small. And then when we get to the air, the step size gets bigger. And as a result, what happens to the ray? Does it keep going in the same direction? Where's it going to go? Toward or away from the normal? Away. It bends away now. It's going to go like this. Oops. I'm having a really hard time drawing perpendicular lines today. Okay. The result of this, here's my theta I, here's my theta R. How do theta I and theta R compare? Which one's bigger? Theta R. So theta I is less than theta R. The ray bends away from the normal. So we're going to come back and do this and actually do some math with this next week and understand exactly how much the light bends But today, because it's Friday and I wanted to do a lab and it seems like a good day to lab it up, we are going to take this knowledge of bending away and toward, okay? And we're going to kind of process that in the same way that we did with our curved mirrors. This is what happens when you have like a flat piece of glass. Are you with me there? But what happens when that glass or that mud or that whatever is curved? Different things happen. So I'm going to just show you real quick that these rules all apply when, oops, I don't even know if it's on there. I don't think it is. Hold on just a second. I'll show you my little picture. Boop, boop. I have to pull it up. I think it was here. When light goes through a lens. So a lens is just a curved piece of glass in this case. It can be plastic, it can be any kind of thing, okay? But we're gonna see literally what happens when light refracts or bends when it goes through lenses, okay? So Shahad has these little lenses. She has pieces of glass that sit in front of her eyes to help her eyes focus all of the light back at her optic nerve so that she can see pictures. There are probably many of you that have little plastic lenses on top of your natural lenses. I just can't see them, so I don't know if you have them or not, okay? And all of us have lenses that are made of tissue in our eyes that help to focus the light by bending it as it goes through a new medium. And that's what we're going to see today, okay? Come up and grab some lab sheets. Why don't you send somebody up from your table to do that? Or everybody can get up, whatever makes you happy. Oops. There it is. So we're going to take a look at a couple of things on here first. And then I'm going to throw you in and have you get some data. So here we go. Lenses are pieces of curved glass or plastic. They can be different things, but ours are glass, okay? That use refraction to create an image. The location to find the image is determined by the lens, okay? And in particular, the lens's focal length. And that's what our goal is in this lab, is to figure out the focal length of the lens. So you remember when we were doing the mirage and we saw that little piggy that was sitting there, right? It was because all of the light was going to that focus, a spot that was at the focal length of the mirror. Same deal here, okay? Except that instead of the light bouncing off, it's going to go through the lens and it's going to create the image on the other side. Now there's a relationship between the focal length and the image and object distances. It looks like this. This is not an equation that you're going to have to memorize. And to be honest, it's not an equation that you're going to see any beyond this lab. But it's a really nice equation to play with, and that's why we're going to do it in this lab. Okay? So I'm going to show you the setup in just a minute down in the, to actually show you what it looks like. But I want to just share with you how you're going to do this. So for each of two different lenses, there's lens A and lens B. Okay? You're going to set up your optical bench, kind of like the picture here. Your object is going to be a lamp, okay? You have a meter stick here that you put a little screen on, and by screen I mean index card, okay? And then you put your lens right here. And the way that you're going to set this up is as follows. And you need to make sure you pay attention. Last period I had a group that was like, oh, we're done, and they'd only gotten about a quarter of their data. So make sure that you pay attention so you know how to set this up, okay? You're going to put the object, which is the lamp, at one end of the meter stick, okay? And then you're going to place the screen or the index card at the other end. And then you're going to move the lens, and I even highlighted it here so that you would see it, and I want you to circle that. You're going to move the lens along the optical bench to find two positions. I want to circle that word two there as well. Slide the lens to find two, count them, two positions where the lens produces a sharp image on the screen. Once you find those positions, you're going to record the image distance, which is this one here, between the screen and the lens, and the object distance between the lens and the lamp, okay? All of the distances are measured from the lens, okay? That kind of is helpful to know. And then you're also going to look at the image and determine whether it's upright, that means sitting up the right way, right? Or inverted, which means upside down, okay? And then also, is it larger or smaller? So you're gonna figure out all that stuff. And then you're gonna move the screen a little closer and you're gonna do the same thing. You move it a little closer, you do the same thing. Keep moving it a little closer until you can't see anything anymore, okay? On the back of your sheet, I gave you data tables. You're welcome. My hope for you, I would like for you all, I think we'll probably do, let's see, 1, 2, 3, 4, 5, 6, 2. I think we'll do groups of 3. And I would like each group to start with lens B. And I'll tell you that again, but lens B is more fruitful than lens A. Okay? And then if you get through that today, then we'll do graphical analysis today. Otherwise, we'll work on that on Monday. Sound good? Okay. So I'm going to turn this off and then I'm going to meet you right back over there so that I can show you how to set this up.